Energy. It's a word we throw around all the time, right? We talk about having it, saving it, using it up. It's what powers our homes, our cars, our bodies. It is, literally, everywhere. But have you ever stopped to think about what it actually is? Let's unbox it.
I mean, we know it when we see it. You can feel the raw, incredible power in a crashing ocean wave, and you can see its quiet beauty in the flicker of a candle. It feels so obvious, so intuitive. But here's the thing. If you had to define it right now, what would you say? And when you use it, like when a battery dies, where did that energy go? Did it just vanish? For something so fundamental to, well, everything, it's actually pretty mysterious. So today, we're going to play detective. We're going to track energy down and figure out its secrets.
So where does our investigation begin? Well, the first big clue is realizing that energy is rarely just sitting still. It's constantly moving, constantly crossing from one place to another. Think of the heat from a stove getting into a pot of water, or the electricity from a wall socket getting into your phone. To get what energy is, we first got to understand how it travels.
And here's where things get surprisingly simple. I mean, for all the mind-bending complexity in the universe, it turns out that energy can only get into or out of a system in two ways. That's it. Just two.
And those two ways are called heat and work. It's actually pretty intuitive. Imagine you're warming your cold hands. If you hold them over a fire, that's heat. Energy is moving because the fire is hot and your hands are cold. Simple. But what if you rub your hands together really fast? They get warm, right? That's work. You're using a force, friction, over a distance. That's the whole difference right there.
Let's drill down on heat for a second. The key phrase here, the only thing that really matters, is temperature difference. You leave a hot coffee mug on your desk. After a while, it's cold. Why? Energy flowed out of the hot coffee and into the cooler air. That very specific flow happening only because one thing was hotter than the other, that's heat. If the coffee and the air started at the same temperature, nothing would happen.
So if energy is moving for any other reason, literally any other reason that isn't a temperature difference, we just call it work. It's kind of the catch-all category. A piston being pushed in an engine, that's work. A windmill spinning a turbine, that's work. Even the silent flow of electrons through a wire is a form of work. It's all about a force acting over a distance.
Okay, so that's how energy gets around. Heat and work are energy in transit. But what about the energy that's already inside something? You know, the energy just sitting there in that mug of coffee before it even starts to cool down. What do we call that?
Well, that has a name too. It's called internal energy. And it is, basically, the grand total of all the tiny microscopic bits of energy buzzing around inside an object. It's the secret life of matter, the energy it holds just by existing.
So what is this internal energy made of? Well, the first part is motion. See, at the atomic level, nothing is ever really still. The molecules and atoms that make up literally everything are in a constant state of frantic, chaotic movement.
And it's not just simple movement. It's a whole microscopic dance party in there. You've got molecules zipping from place to place, spinning around like tiny tops, and the atoms inside them are vibrating like they're attached to little springs. All of that jiggling and moving is kinetic energy, and it's a huge part of what our clumsy human senses perceive as heat.
But that's only half the story. Internal energy isn't just about motion. It's also about potential energy, the energy that's locked away in the very bonds that hold all that matter together.
And this is huge. The chemical energy in a log of wood or a gallon of gasoline, that's energy stored in the bonds between atoms. But then there's the really big one, nuclear energy. That's the colossal amount of energy locked away in the bonds holding the nucleus of an atom itself together. Releasing that is how we get nuclear power.
So, we have our clues. We've got energy on the move, heat and work, and we've got energy in storage, internal energy. The final question for our investigation is, how do they all connect? And the answer is one of the most important and fundamental rules in all of science.
Let's frame it like this. If you take a system, say a can of soup, and you add energy to it, either as heat by putting it on the stove or as work by shaking it really hard, what happens to the energy inside that can of soup? Does its internal energy go up? And by exactly how much? Turns out there's a law for that.
And this is it. The big one. The first law of thermodynamics. It is an unbreakable rule of the universe. You cannot make energy from nothing. You cannot make it disappear into nothing. You can only, ever, change its form. Every single bit of energy has to be accounted for. Always.
The easiest way to think about this is like a bank account. It's literally a bank account for energy. Any heat
or work that flows into your system is a deposit. Any heat or work that flows out is a withdrawal. And the change in your balance at the end of the day, that's the change in your system's internal energy.
It's a perfect accounting system. You just track what goes in, you track what comes out, and the difference tells you precisely how much the energy stored inside has changed. Nothing is ever lost or gained, it just moves around and changes form.
Now, this isn't just some abstract idea for physicists. It's incredibly practical. Because the first law tells us that every bit of energy is accounted for, it gives us a way to measure how well we're using it. It's the key to understanding something we talk about all the time, efficiency.
Efficiency is really just a simple question. Of all the energy I pumped into this thing, how much of it came out as the useful stuff I actually wanted? For a light bulb, the useful stuff is light. For a car, it's the motion of the wheels. The rest is, well, we'll get to that.
Just look at this table for lighting. An old-school incandescent bulb? Not so great. It's pretty terrible at its one job. But look at the jump to a compact fluorescent. That's why you can replace an old 60-watt incandescent bulb with a 15-watt fluorescent. It's because the fluorescent one is way, way better at turning electricity into light instead of something else. Now, here's a fun one. You look at this chart, and it's a no-brainer, right? The electric water heater is 90% efficient, while the gas one is barely over 50%. Case closed. But wait, efficiency isn't the whole story. Because natural gas is often way cheaper than electricity, that less efficient gas heater can actually cost you less money to run. So the first law gives us the efficiency number, but real life adds other layers, like cost.
So, let's do a quick recap of what we've unboxed. The universe has a strict rule. Energy is always conserved. It never, ever disappears. It travels around as either heat or work, and it's stored inside things as internal energy. And this one beautiful, simple law is what lets us keep track of it all and engineer a more efficient world.
But that leaves us with one final nagging question. If that old incandescent light bulb is only, say, 5% efficient at making light, and we know from the first law that energy can't be destroyed, where in the world did the other 95% of that electrical energy go? The law guarantees it's still there somewhere, but in what form, and why can't we use it to read our book? That is a fantastic question for another time.